Hello, hello, hello. We're back again. Tackling more problems in our problem-solving videos now. So, more with evaluating weird limits, right? Now, this is a weird function, but I personally like it a lot. It has some interesting properties, and overall it's not that difficult once you understand it. So, let's begin. Again, the first thing you should always do when evaluating a limit is just try to plug it in, right? So if we plug in 1, we get absolute value of 1 minus 1 over 1 minus 1. And yeah, this is going to output 0 over 0. And again, that's an indeterminate form. We cannot accept that as an answer to this limit, right? Now, in the last video, we looked at factoring, right? Factoring numerator denominator as a way to find holes in our function and rewrite our limit in simpler terms, which sometimes allows us to plug in our input value to a slightly altered function and overall come out with a real number for an answer. I don't know about you, I don't think I can factor this. I don't want to try, so let's not. Also in the last video, I talked about what a limit really is again. Remember, we are approaching 1. We are getting really, really close. So remember, think about plugging in x equals 0.9999 into your function and x equals 1.0000 and then 1, right? We're getting really, really close. And sometimes we just have to do that in order to solve our limit, right? So with problems like this, where you get an indeterminate form if you just plug in the input, where it doesn't look like you can simplify your function at all, I'll teach you a new trick here. Remembering back to one of our very first videos, where the limit of a function will have left limits and right limits, right? Now these come in handy with these weird evaluations here. And sometimes we have to do a little bit more work in order to get a convincing or a real answer, right? So I'll start off here with a left-hand limit. We'll be approaching 1 from the left side, right? So we'll be using these numbers. And then writing out my function again, because it is the limit of this function as x approaches 1 from the left, right? Now let's go ahead and plug in this number, right? We're plugging in 0.999, I'm just going to stop there, minus 1, and absolute value of that, over 0.999 minus 1, right? And you can do that by hand, you can do that in the calculator, but with this function, a trend you'll notice is that if this numerator, if you ignore the absolute values, outputs a negative number, right? The absolute values will turn that into a positive number. But the denominator will still be a negative number because there is no absolute value bars there. So in this case, the numerator and the denominator, however, will be equal, right? I believe this is 0.001, right? Yeah, you could do that in your head. What we're going to end up getting is absolute value of negative 0.001 over negative 0.001. And that's just going to equal negative 1, right? And we could do this with any number to the left of 1. You could plug in 100, or my bad, negative 100. You could plug in 0.9999999, right? You'll always get negative 1 if 1 is larger than whatever you're inputting. Now the same thing goes with our right-hand limit. So as we approach 1 from the right side, x minus 1, or absolute value of x minus 1 over x minus 1, and I'm going to plug in just 1.001 minus 1, and 1.001 minus 1, right? And this is going to get us positive 0.001 over positive 0.001. And that just equals positive 1. So the trend here is, with this function, this kind of base, minimally transformed function, we will always see -1 on the left side of 1 here, and +1 on the right side here. But also notice something. Here, our left-hand limit, and I'll draw this in blue, does not equal our right-hand limit. Well, it looks like a smiley or frowny face, right? The left-hand limit does not equal the right-hand limit. So first of all, this limit does not exist, right? But we can use this information, oh, sorry, that's my cat. We can use this information to visualize a function. Now I have it drawn here. This is what this function looks like. It's a pretty fascinating function. It looks like almost like a staircase, steps, right? If you remember back, transforming functions, subtracting 1 is of course going to shift it right 1, which is what happens here. This function is kind of centered around x equals 1. But notice that I have holes here, right? Now remembering from our last video, holes, not vertical asymptotes, but y, right? Kind of proved it up here. We plugged in a value very, very close to 1 on both sides. And our function did not shoot down or up towards positive or negative infinity, right? So we're going to have holes instead of vertical asymptotes. Now, if you remember continuity, I believe this is the exact example I used to show a jump discontinuity, right? This is a jump discontinuity. What's more important is that we have 2 holes here. Our function is undefined, but has real left and right hand limits. If we were to plug in 1, get 0 over 0, that's an indeterminate value, and I don't see another way to simplify this function. So here I just have a few examples. If we were to plug in f of 0, right, if this is our f function, you can see it right here. It's going to be -1. But if you want, you can solve this. You're going to get absolute value of 0 minus 1 over, and then just -1, right? And that equals -1. You get +1 over -1, that gets you -1. Same thing here. The pattern continues, except since we're to the right of our center, we're going to have a value of 1, or output value. But here we go, f of 1. This doesn't exist, right? We can ignore this for now. You could say it does not exist, right? DNE, cross it out. Function does not exist at the center, x equals 1, right? But overall, to conclude, sometimes we get wacky limits like this, and there's no way we can simplify them. We can't just plug in our input value because we get an indeterminate form, and that leaves us with really only one option, and that's plugging in values really, really close to our intended input on the left and right side to hopefully find what our function does as it approaches 1, right? So I have nothing else for you today. Thank you very much for joining me. Goodbye, class.